So one of the things I want to do when I'm launching the hardware simulator is I want to extend the bottom border as I just did. In case any error messages show up here, I can deal with them. What we were looking at the close of our class on Wednesday, we have some built-in chips, and was one of these. And then or actually not was one of these. I think I had not open. Did I not have not open? Okay. And I showed you a case where we had a NOR, and the NOR took the output of the OR and fed it in. Does everybody remember this?
Yes.
And
Yes.
this is a case where the output of OR, you'll notice that there are two sets of A's and two sets of B's when you start mixing logic gates to build compound or complex logic gates. So when we're looking at NOT, and we're looking at AND, these are all pretty simple. And by convention, I want you to know that your author uses a type of shorthand to express the logical behavior, which is similar to pseudocode you may write. We talked quite a bit about that in our last class, right? But as a convention, your author, when they built this simulation environment, which by the way mimics the hardware definition language and logic gate simulation, virtual simulation environment that you find in fabrication facilities, right? So factories for chips have this design software, and it's many thousands of dollars, right? So this is one cool reason why we chose this textbook, is because the authors came up with their own version of this, and it works in an identical fashion to the commercial product that you find in Intel and NVIDIA and in AMD. By convention, the author uses A and B to indicate the input pins, okay? But there's nothing to prevent you from changing that. So you could change it to, and I'm going to do this, I'm going to save this as, so this is called progress by revision. When we take something and we tweak it, we're going to save it as, and I will call this and version 1, okay? Everybody with me?
Yes.
And I'm actually going to make this capital, right? So this is and version 1. And it's not going to work unless I change the chip name to match the file name. I'm going to get an error. Let's look at how that error would present, okay? If I try to load this in the hardware simulation environment, and I go to load a chip, and I go to AND version 1, it's going to say, hey, the chip name doesn't match the HDL name. Everybody see that?
Yes.
Yeah, that's a common error. And how do we fix that? Well, we change this so that it's AND V1 and V1 up here in the comments. Why in the comments? So we don't lose our bearings, right? And I could say revised by T. Kentop on 16 September, right? So somebody would know, okay, who was messing with the Kool-Aid? Now I'm going to save this. And if this works properly, the same logic should hold true and it should run. So that's what I'm going to do. I'm going to go back in here in my simulation environment. I'm going to load the chip. It's going to be AND version 1. I'm going to see listed inside here the HDL that's used. I see my modification here, right? And the chip name is AND V1. And if I put in 2 true values, I should get, just like any other AND, when I run this, I should get what right here? What should I see?
1.
A 1, yes, correct. And I see a 1. And so, let's make sure it's really working like an AND. If I change the input of the A pin to false, when I run it again, what should happen to the output value?
V0.
It's going to flip back to 0. Yeah, thank you. So it flips back to 0. So I have a way of validating that that change did not cause a problem. Now, what I'd like to do is modify this a little further and create AND V2, right? So I'm going to save it as AND V2. And again, I refer to this save as method as progress by revision. Because if I make a mistake in this next set of changes, have I lost the first set of changes that actually work?
No.
No, I have not. I have not lost the next set of changes. Now I need to take care of business or I'll have an error. Okay. So I'm going to change this to 2. But now I'm going to mix it up. I'm going to make this M and N. Well, let's say that I'm dealing with a chip that has a lot of pins. Like everybody's seen CPU chips, right? They have lots of pins on the bottom. I mean, they have hundreds of pins. Everybody knows what I'm talking about, right? Maybe?
Yeah.
Okay. So by convention, the authors use A and B. And that's significant because they just tend to stick to A and B all the time. And that gets a little confusing when you start combining chips because what you end up with are cases like this. Does everybody see the A and the B?
Yeah.
That's for the whole chip we call NOR. So there are 2 pins going into the NOR. And there's only one coming out. And they decided to call the out pin out. But once you get inside here, a NOR is a combination of a NOT and an OR. So the A pin of the OR inside the NOR feeds into the A pin of the NOR. The B pin of the OR feeds into the B pin of the NOR. That's why you say A equals A, B equals B, and out equals W1. Now, what does W1 mean? Like many software development scenarios, when you're creating software, it is quite common for an intermediate result to be stored in a separate variable until it's used in the next step. Does everybody know what I'm talking about? So you're developing software. There's a programming statement that executes. The output of that programming statement is stored temporarily in, it's like a separate variable just for the short term until it is used in a next programming statement. Does everybody understand what I'm talking about? You have
Yeah.
intermediate steps, right? Intermediate steps. the same thing is true in the hardware level. What are we saying? In this version of NOR, the A and B inputs of OR receive the possible combinations of ones and zeros, and the out is fed into a temporary, it's an intermediate pin or wire. We refer to pins and wires synonymously. When it comes to logic gates and chips, a pin is a wire is a pin, okay? A pin is a short wire. Everybody understand what I'm talking about?
Yeah.
Okay, so we're going to say that the out of the OR is going to be called W1. Now, look at what happens next. In this version of NOR that is in this version of an OR and a NOT that are combined to create NOR, in this most common version, the output of the OR is fed into W1, and then the W1 is fed directly into the input pin of the NOT. Does everybody understand what's going on here?
Yes.
Kind of, sort of. Let me draw you a diagram, okay? And then I'm going to turn my camera on and I'm going to swivel it around, and I'm wearing my funky glasses today, and it's a Friday and I didn't shave and I was in a hurry, and I'm not very photogenic, which is why I put this stuff down, but I'm going to draw an OR going into a NOT, and I'm going to exaggerate here. It's going to be kind of like the drawing I had before. All right. I'm doing it on a whiteboard now. All right, everybody ready?
Yeah.
Drum
Yeah.
roll, please. Okay, here we go. There we go. Hey, how is everybody? Woohoo! Yeah, I was in a hurry this morning. Everybody see that right there?
Yeah.
Yes.
That says
Yes.
it says W1, doesn't it?
Yes.
Now, is that backwards? Is it showing backwards? I can reverse the camera input, but basically what you have, what is this logic gate right here?
Or.
And what is this one here?
Not.
Yeah, exactly. And in between the OR and the NOT, this is the output pin right here. And we've called that output pin of the first logic gate W1. That's why we labeled it W1. Now, what does that become? The input of the NOT. It's an intermediate step and an intermediate connection. And that's important to understand when you're combining logic gates, right? If you don't have that understanding going into it, then it becomes trouble. We call this the implementation view, okay? So this is the implementation view. And basically what we have here is a larger logic gate we would call this the NOR. So the larger view is called the interface diagram. It looks a lot simpler. I'm just doing it in dotted lines, superimposing the simpler interface diagram over the implementation diagram or implementation view, okay? If I were drawing it simply enough, I gotta take this up here. I'm just gonna make it like this, right? I'm gonna have two inputs, and now my dry erase is running out. Perfect. Well, it's a Friday, that's good. Everybody see that?
Yes.
Yeah.
So that's a typical NOR. That's like a standard implementation of a NOR, and this is the interface view or interface diagram of a NOR. And what you're getting down here is the inside guts of it. We call that the implementation view. Don't forget W1. Everybody, repite usted, por favor. W1. Any questions about the diagram I just shared?
No.
Okay, I'm going to bring my tablet next time so we can draw live and then share the tablet screen, and that might work better. And then you don't have to look at my ugly mug. Okay, all right. There we go. Any questions about what we mean by W1? Now, we are dealing with a different version of the not or, okay? In fact, as we left this last Wednesday, we are dealing with a, before I forget. And version 2, right? Did I not change M and N? Well, I changed A and B to M and N. Does anyone want to see if this runs just as well in our simulation environment?
Yes.
Yeah, let's do that. I'm going to save this because I got to save it. And I actually did a save as, right? Because I made these changes and I wanted to know, all right, is that one change going to muck up the works? So I'm going to go ahead and run this by loading the chip. And I'm going to do a and version 2. Oh, look, M and N instead of A and B. M and N, there's the V2, there's the V2, right? Everything matches. Let's see if it behaves like it's supposed to. I'll put a 1 and a 1. Did you know you can actually test each truth variable possibility and execute it automatically by running a script? You can actually feed combinations of ones and zeros into the M and N in one giant script. This environment is incredibly sophisticated given it's open source and free, right? So what am I saying? You can take each of the possible combinations, 0 and 0, 0 for M, 1 for N, then flip it. 1 for M, 0 for N, and then the last combination, 1 for M, 1 for N, and you can fire off that script and it'll feed them in, execute, feed them in, execute, compare the values to see if they match the truth table. It's a script-driven testing process, right? Very cool. Very, very cool. Anybody wants to do that for additional credit, just to noodle around with it? You have references with NAND to Tetris. There's probably some videos on how to run that script. In fact, I know there is. If you want to do that just for grins, you're welcome to do that. The point I'm trying to make is you can change up some of these things to reduce confusion. Because to me, this scenario right here is a little confusing. A equals A, B equals B. Well, it's easy to get lost in the A's and B's. Does everyone understand what I'm saying?
Yeah.
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 It tends not to work when you mix up the case. It shouldn't be case sensitive, but I think it is. It doesn't work as well if you mix up the cases. So whether it's capital A or little lowercase a, you have to be consistent all the way across. Otherwise, it won't work. Now let's get back to the other drawing that we had, right? We had another drawing that we were doing in class. I showed you. Not or, this one. Everybody remember this?
Yes.
Okay.
Yeah.
This,
Yes.
in this case, I'm using a single not and I'm using an or, but the outcome is different. I don't get the same result in the same manner or in the same sequence that I would if I put the not out here. So what I have to do is build the HDL to create this And I already have my logic statement. Remember, we already performed this. We did the truth table, we did the canonical, then we took the simplest case of the reverse canonical because there was only one output that was false, right? There was only one output that was false. And we identified that when one of these was true and the other one was false, the output was false. There was a single case. Does anybody want to see that again?
Yes, I want to say that again, Dr. Kentop.
There's always someone. And
Yeah, I came late.
no, I'm glad that I am glad that we are reviewing this just briefly, right? So I think it's this one. So here you have a software function, right? This is a Boolean function. If we were doing this in software using Boolean operators, instead of with logic gates, we would have, actually this is an and instead of the or. Was it the example one that was or? It was example one that was or, my bad. Example one was or. Yeah, there we go. Or. And the B input is knotted. So it's B bar, right? And we did the truth table in one of two manners. So we did it where we put the values after the not executes to the side before we ORed the two results. Or the other option was we had a separate column that showed these two, and then we put this in bold and this in bold, so we knew that this was kind of an intermediate step. So we added a column. That's the other way of doing this, right? And then we combined. We have an or between a 0 and a 1. Well, that's a 1. We have an or between a 0 and a 0. Then we decided, okay, let's do both the standard canonical expression and the reverse canonical expression. Well, if we want shorthand and we use the standard canonical expression for every case that's true, we have to come up with 3 separate statements for the original input values, the original ones, not the ones after not, but the original input values. So in this case, I have an A tick, B tick. Everybody understand where I got that, right?
Yes.
And then this is a 1, so this is A, B tick, right? And then here I have A, B, right? Well, that's not really shorthand if I have to write, I mean, some truth tables get very big, right? Some have 9 sets of inputs, some have 16 sets of inputs, some have 25 sets of inputs, right? It gets very big very quick. Number of inputs squared is the length of the table. All right. So all we have here is the reverse canonical expression. That's the simplest, A tick B. The outcome is false when A is false or 0 and B is true. That's what we have right here. A is true and B is false. And even with all the extra steps to make sure I don't miss it, I actually missed it and I misstated this and a student caught that, right? So it was really good. And here's our logic statement, right? Now, is everyone caught up?
Yes.
Yes.
So if A is equivalent to 0 and B is equivalent to 1, then out is 0. Otherwise, out is always equal to 1. That's the logic statement. And this is kind of in pseudocode fashion. Now, how do we build our HDL stuff? And I've just showed you some of the tricks, right? So now I go into my, whoops. I go into my tools. I'm going to start my hardware simulator again. And understanding that based on the canonical expression, the diagram, and the logical statement, I just showed you that diagram, right? We still have that diagram right here. So what I have to do is build out the HDL to show that my NOT is going to receive input, but then the output of the NOT is going to be what? Based on the previous example I just shared with you. I had a NOR on the screen. Based on this, what am I feeding into the knot? Or what comes out of the knot? See, the knot in this case is on the front side. It's on the input side. It's not on the output side. So how could I change this statement? This is what a typical NOR is built like. But I said I wanted to create a, what was the name of it? What did I call it? I wanted to call it something different so that I understood that I wasn't dealing with a common NOR. Was it NOR and? No. Let's do
Not
that.
or?
It was a not or. Everybody see that?
Yeah, I see it.
Not or. And the other problem is that when I saved this, I was in Notepad and I started doing this kind of thing. So one of the things I got to do here is sort of change the extension from TXT to HDL, right? Otherwise, I'm going to save this as a not or. And instead of using a TXT, I'm going to change this to HDL because otherwise the simulation environment doesn't know what to do with a text file. Does everybody understand what I'm doing here?
I think you didn't make a not on HDL already.
Yeah, I did make a not or already, but it might have been a different not or. So I want to make sure that yeah. There was another HDL that was not or. There was a NAND or. There was a NOR and. There was an or and. Things got really interesting last season, okay? But what I'm going to do is stick to so I'm going to sort by the latest. All right, so there I am. Yeah, do I have multiples of these? Better close all this off and make sure I don't have multiples open, because then I'll make a change in one window and forget to make a change in the other. All right, so there's a couple of things I need to do to make this work. If it's going to be a not or, I see some inconsistencies. This is correct. But in order to make this really proper, I'm going to do a save as not or. And if I refresh, oh, come on. Really? I wanted to be case sensitive, right? So this is not or, and I'm going to say not or here. Does everybody understand what I'm doing now? So according to my diagram, I still have A and B inputs for the not or. I'm gonna keep that convention, okay? Everybody with me?
Yes.
Yeah.
Okay, so there are two inputs. So this first part of the HDL language tells me, okay, how is the big chip, the whole chip, going to work? Well, there are two inputs, A and B, and there's an out we're going to call out. I'm not going to change that. But there are parts. And I'm going to switch this up. The or doesn't come first. The not comes first. Well, yeah, so there's something going on here with the B, and I have to account for what's happening here before I even look at what's happening with A and B with the or, okay? Does everybody understand what I just stated?
Yes.
Yes.
So I'm going to put the not first, and I'm going to say that what's the input? What is the input for the main chip with not right here? Is it A or B?
B.
B.
It is B. That is correct. So I'm going to say in is B, And that's a reference to the main B, which is right here. Everybody got me?
Yes.
And now the output, if I draw this out, if I explode this view and I use a whiteboard like I just did, I'm going to have an intermediate step because I have output from the knot that gets fed into the B of the ore now. So what am I going to put for out here? What's sitting in front of this knot that you don't see?
W1.
The W1, correct. Does everybody understand what I'm saying? Should I show you the other picture again?
No,
Everybody get it? Okay. So if I were to take this and explode the view, I'd have the B input pin, I'd have the knot, and then coming out of the front of the knot would be a W1, and then the W1 goes into the B of the ore, right? So,
Yeah.
so the A of the internal ore feeds into the A of the internal ore. This is really clean, right? So in terms of the big chip, the main A feeds into the smaller A of the ore, okay? But the B, what do we put here?
W1.
W1. And then what do we put here?
And out.
So the out of the ore becomes the out of the not ore. Out equals out. So to recap, the A input for the not ore feeds directly into the ore. That's what we see right here, right there. The B input hits the knot first, and what comes out is W1. That W1 feeds into the B of the ore. That's why it's listed down here under ore. And what comes out of the ore comes out of the not ore as a whole. So there's two kinds of knots. There's an out. I mean, there's two kinds of outs. There's the out for the not ore, and there's the out for the ore. Does everybody understand what I'm getting at?
Yeah.
Yes.
Okay. So what I'm going to do is save this, load it, and see if my values match what's in my truth table, this truth table. I got to check this out. I mean, in terms of the software version of this, I already know what I'm supposed to get, right? If I put in a 0 and a 0, I should get a 1. If I put a 0, but the B is 1, I should get a 0. Everything else should be 1, which is kind of weird, but hey, by intention, by design, you could have a situation, and this is where I'm going to lean in close and explain. Are there cases where it's like, yeah, if this is true, but that's false, you want to have current flowing. In other words, you want a true when one thing is true, but the other is false. Take, for example, somebody sitting in the car seat, driver's side. Are you with me?
Yeah.
Yes.
There's a weight sensor. Did you know there's a weight sensor in your seat in the driver's side by law? There's also a seatbelt sensor that says, hey, it's hooked up or it isn't hooked up. So if I have a driver sitting in the seat, but the seatbelt is not fastened, then what happens to the warning light? Is it on or off?
On.
It's on. Yes, exactly. So what you're doing is designing a chip that saves lives. You're designing a chip that has a singular purpose. It's like, okay, if I have a passenger and the seat weight indicator is on, but the belt indicator is off, then I have a warning light that says, hey, you got somebody in the seat, and this alarm light is not going off until somebody puts their seatbelt on. You get what I'm saying? All right, now I'm going to go ahead and load this chip, and in the 2 minutes that are left, we're going to see if this works. So I have a not or this one. Says chip name doesn't match the HDL name. Remember I was talking about case sensitive? Everybody?
Yeah.
Yeah, you're seeing the end result here, aren't you? Kind of goofy. All right, all right. So you want to be picky. You want to be picky. So I'm going to open this up. And well, actually, I'm going to close this. And then I'm going to open it up again. No, I'm sorry. I'm going to be in the here. I'm going to change this so it's lowercase r, so it matches. I'm going to change this so it's lowercase r, so it matches. I'm going to change this so it's lowercase r, so it matches. Everybody with me?
Yes.
Okay. Now, let's go back to this. And here we go. Going to run this as administrator. Going to load the chip. Going to find the not or. Ah, no error. I'm sorry. I didn't mean to like blow out your ears. Everybody see this?
Yeah, we see it.
So what's the case we're testing for? The one case that's false. It's going to be when A is false and B is true. I should be getting a false. Everybody see that?
Yeah.
Because it's already
Yeah.
giving me the first case. The value is 0, the value is 0, and the output is 1. I've already done this first case. The output is 0, the input is 0, the input is 0 before it's flipped with a not. That's 1. I already have one case resolved. Let's put a 0 in A and see if it changes to 0. A 0 in A, was that 0 in A and, yeah, B in 1. So I'm going to put a 1 here. Instead, I'm going to execute. It should flip to 0. Run. Yes, it changes. But let's make them both 1. And run it. Should be 0. No, it should be 1. That's right. Let's make them both 0. We already did that. That was the first case. 0 and 0. Let's see. The one thing we haven't done is A is 1 and B is 0. It should be a 1. Did we already do that?
I don't think so. I think we did the 0 and 1.
A is 1 and B is 0. So A is 1 and B is 0. And it should still be a 1 if I run it. And it is. It's still a 1. So here you see that the hardware device simulation environment, right? HDL, hardware definition language. It tracks with your truth table. It tracks with your canonical expressions. In most cases, it's easiest and it's the direct flight to just use the simplest, shortest expression with the logic, right? With the truth table and with the behavior of the chip. The only difference is the chip performs 1,000,000 times faster. No exaggeration. Any questions before we close today? All right, on Monday, we're going to take a 3-input, 3-logic gate example. We're going to take it up a step. But for your solution for module 2, you need to design a basic combination of 2 different logic gates, your own invention. You want to draw it out. You want to create the truth table. You want to do the canonical. You want to write the logical expression, and then you want to take it to the hardware simulation. That's what you're doing for your solution in module 2. We're going to practice a little more on Monday before we do that. But you can start noodling by drawing. What am I saying? I want you to start getting ready for next week to take on the solution. And we're going to have like sessions in class to walk people through that, right? We're going to walk you through this, crawl, walk, run. You're going to do your own complex, basic logic gate with 2 different, okay? 2 different, could be an and and an or, could be a not and an or, could be a not and an and. You're going to come up with something different, okay? Any questions before we break for the weekend?
No,
Going once,